Hello class, in this video I'll be showing you how to find inflection points and how to use the test for concavity. Let's begin. Find the inflection points, then determine the intervals where the function is concave up or concave down. And here is the function we're going to work with. It is m of x. Now I've already gone ahead and provided the first derivative, and I'm going to show you how to take the second derivative, because the second derivative is what's needed to find the inflection points and the intervals in which the function is concave up or concave down. So here is the second derivative. And we know that the possible inflection points are where the second derivative is equal to 0 or the second derivative does not exist. So I'm going to set the second derivative equal to 0. And I'm going to solve for x. And that reduces to 3/2. And this is the location of a possible point of inflection. We will determine later if this is actually an inflection point. Okay, so how about the question, second derivative does not exist? Well, in this case, the second derivative exists for all x in the domain because the second derivative is linear. All right, so the only possible point of inflection is at 3/2. So what I'm going to do is I'm going to make a chart. And since the point of inflection separates concave down from concave up, so it's the point where concave down changes the concave up or concave up changes the concave down, I'm going to create two intervals. The first interval being -infinity to 3/2. That'll be the interval before the inflection point or the possible inflection point. And 3/2 comma infinity will be the interval after the possible inflection point. Now what I'm going to do is I'm going to pick a random number in each of these intervals. So in the first interval, I'm going to pick 0 because 0 is easy to work with. And in the second interval, I'm going to pick 2. So the second derivative is equal to -12x plus 18. So I'm going to substitute 0 in for x, and the result is 18. So that means the second derivative is positive. So the original function is concave up. I'm going to do the same thing with the +2. And this results in a -6. So the second derivative in this interval is negative. So the second derivative is, so the original function is concave down. Now, since the function changes from concave up to concave down at the point 3/2, we can conclude that 3/2 is an inflection point. So x is equal to 3/2 is a point of inflection. M of x is concave up in the interval negative infinity to 3/2, and m of x is concave down in the interval 3/2, comma, infinity. Okay, now I'm going to show you in Desmos. So here's the graph, and over here in the top right-hand corner, there's a wrench. These are the intervals that I've used, so about negative 24 to 43 for x, and then negative 427 to 936 for y. Feel free to change those up. And what I'm going to do is I'm going to evaluate f of 3/2. And it looks like that's 525 halves. So now I'm going to write out the coordinate 3/2, comma, 525 halves. Going to label it. And you'll see on the graph that the coordinate 3/2, comma, 525 halves is clearly the point in which the function changes concavity. So it looks like it goes from concave up to concave down at this point of inflection. So here, I'm just going to add a little bit of information. I'm going to write this as 3/2, comma, 525 halves is the point of inflection. And now we are done.